So the next section is devoted to vector equations. Now you might be able to guess what they are already. A vector equation is simply an equation where the left and right hand sides are vectors. So what is a vector? That will be a natural place to start. So we'll start by introducing some terminology. So a vector, one way to precisely define a vector is just to define it as a matrix that either has only a single row or a single column. So in the case, if you have a matrix that has only a single row, then we call it a row matrix or a row vector. And if you have a matrix that has only one column, well, then you call that a column matrix, or similarly, you can call it a column vector. And there's no real difference between row vectors and column vectors other than the way that they're written down. One point of view would just be that a vector is a vector no matter how you represent it, but there's going to be some situations where it's convenient to represent them as columns and other cases where it's convenient to represent them as rows. But for the moment, we're going to stick to mostly representing them as columns, and I'll talk more about that in a moment. But one last thing we'll throw in here. You may have heard me already use this word, but now we're going to precisely define it. A scalar is just a real number. Okay, so this is you may have often, or many of you may have heard of vectors before this course in some context, and one of the most common ways for them to be introduced as they're introduced as objects that have two main attributes, a magnitude and a direction. But scalars are usually contrasted with that as in failing to have any sort of direction. They're just, all they are is a numerical quantity. Okay, a couple of quick examples. So this is an example of, right here, this is an example of a column vector or a column matrix. I'm going to just say a column vector. So, and actually, why don't we be a bit more specific here? Why don't we move this over and say is a four-dimensional column vector? Okay, because it's a column vector because, well, it satisfies this definition, right? It's a matrix that has a single column, and it happens to also have four entries in that single column, so that's why it's referred to as a four-dimensional column vector. Now, this example here, this is an example of a row matrix or a row vector, but there's only two entries, so this is referred to as a two-dimensional row vector. So that's all there is to that notation. And like I said, a vector is a vector independent of how you decide to write it down. So there's lots of different notations that you'll see vectors written in if you go, specifically or in particular, if you go outside of this course and you maybe read other textbooks or you take another course or you see them in some other context, whether it be an academic setting or more of a professional setting. But here are some examples of different notations that can be used to represent the same three-dimensional vector. Right? This is a three-dimensional column vector. It's got coordinates 3, 0, and 2. Here's the same vector written as a row vector, and it's got coordinates, the same coordinates, 3, 0, and 2. Okay, notice this one here. It's kind of similar. I've written them using square brackets, although it's a little bit more compact. But there's commas that are written in between each coordinate. Well, by separating the coordinates with commas, that gives me a little bit more flexibility not to have to spread them out so much, right? Because if I take this notation, for example, if you were to compress this notation so much, you might not be able to tell the difference between, well, is that a 3, a 0, and a 2, or is it just 302? Maybe it's a vector with one coordinate, a one-dimensional vector with a single entry of 302. There will be some room for ambiguity and confusion there. So that's why when you see a vector written in row form like this, the entries must be very spread out to prevent any risk of the entries blurring together. But if you separate them by commas, well, then there's no problem. Now, but then the next question is, well, do you have to use square brackets? Well, there's no reason why you should have to use square brackets. Why not use angle brackets here? Or here we've got round brackets. And you'll see a variety of notations used to represent vectors. Like as this comment says right here, for now we'll stick to column matrices. So for now we'll just for the simplicity, let's use the same notation most of the time. And that notation that we'll stick to is using column notation to write down vectors. Okay, so a few other comments about notation. We'll typically use bold letters in this course to represent vectors. Now, this is actually not what I normally do. I like to write them with little vector arrows on top. So this is a personal thing. I'm not going to expect you guys to do this, but typically I would write a vector like this, and books that I've used in the past adopt that notation. But since our textbook uses bold letters instead, we're going to go with that, right? I want to be consistent with the notation that our textbook uses. So for that reason, we'll stick to just using bold letters. So like you see here, notice I've got the X and the Y are in boldface. It just helps to make sure that they stand out as vectors as opposed to other values. Okay, now I mentioned this is a 4-dimensional vector, and this is a 2-dimensional vector, and this is a 3-dimensional vector. There's no real limit to the number of coordinates your vectors can have. You can have a 17-dimensional vector if you want, or you can have a 9-dimensional vector if you want. And that leads to a natural question. Well, how can you have something that has more than 3 dimensions? And the answer is easy. Just add another coordinate. Now that may feel like cheating because it's difficult to imagine what these things would look like. But just because you can't imagine what something looks like doesn't mean you can't write it down and use it mathematically. So don't be too restrictive in your understanding. Don't make the assumption that vectors can't have more than 3 coordinates. Okay, we can have vectors in higher dimensions, and a lot of this course is devoted to topics where we will do exactly that. And before the end of this section, you'll see a concrete example of where you might use 4-dimensional vectors and work with them algebraically, even though you can't actually draw them. So anyways, I'm digressing a bit. Back to the notation bit. This blackboard R, remember the blackboard R stands for the set of all real numbers. If I just put an exponent on that, so if imagine n were 2, well, then we'd have R2. That's the set of all 2-dimensional vectors. If I have R3, well, then that's the set of all 3-dimensional vectors. If I had n equals 7, well, that'd be the set of all 7-dimensional vectors, and so on, right? So it's just a way to describe a particular class of vectors. It's sometimes referred to as Euclidean n-space or n-dimensional Euclidean space. Okay, now let's say you had a particular n-dimensional vector, and let's stick with the notational convention we said above, and we'll give it a bold-faced letter as a symbol. So we use boldface X here. So if X is an n-dimensional vector, then you can write this notation, which just says that X belongs to Rn. It means it happens to be one of the vectors that lives inside of Rn. And remember, Rn is just the set of all n-dimensional vectors. So if n doesn't have n entries or n coordinates, if it's got some other number of coordinates, so maybe it's x, or pardon me, maybe x is an n-1 dimensional vector or an n+1 dimensional vector, well then it wouldn't be an n-dimensional vector, in which case we will say that it doesn't belong to Rn. So let's maybe write down a couple of examples so I don't have to, so it's not so abstract. So for example, if I had the vector x, let's write down a 2-dimensional vector. This is an example of a vector that is in R2. But if I write down a vector y, and I'll give it 4 coordinates, 1, 0, 1, 2. That is an example of a vector that is in R4. But this vector x up here, I would not say, or specifically I would say that x is not in R3, because why? Well, it doesn't have 3 coordinates, right? It only has 2 coordinates. So it does belong to R2, but it doesn't belong to R3. And then similarly with y, I can say, for example, that y does not belong to R7. Why not? Because it doesn't have 7 coordinates. It's a 4-dimensional vector, not a 7-dimensional vector. That's all we're saying. Okay? And 2 vectors in Rn are equal. Well, when are they the same vector? If all of their coordinates are identical. That's the only case where 2 vectors are considered to be the same vector. If even a single one of their coordinates differs, then they're different vectors. That's all there is to it.